The main theme of this course is understanding the modeling issues, carrying out the effective simulation for the medical devices, and primarily we are talking about the respiratory and cardiovascular assistance devices. I'm Rakesh Mishra, and I work at University of Hudders-field, UK, and I'll be delivering majority of the material for this particular course. I'll be supported by Dr. Tiwari in explaining the safety features for this particular course. The course has following features: developing an understanding of medical devices. I hope you all have a reasonable understanding of medical devices. So we'll discuss about current issues with regard to the medical devices, standards, safety, performance, faults, and all the aspects. How the functionality of medical devices, how the functionality is improving. So we can see from the last so many years how functionality has improved, and the new technological breakthroughs, they have made lots of challenges easier for human life. Performance evaluation of medical devices. Earlier, like having medical device was a big thing, the cost wise and the application wise. With the advent of technological breakthrough, the performance have gone a lot better, like very simple blood pressure measuring machine to a very devices that are tailor made for particular application. So this has improved drastically. Medical devices by nature are very severe service applications, and unfortunately if you have a bad ventricular assist device, something going wrong can be quite fatal. So we need to continuously monitor the performance of the medical devices. So any fault by the how do we monitor the fault on the medical devices, that needs to be understood. So fault diagnosis is a part of it, and in this particular class we will go through the fault features. If there are faults in the system, how we can predict that this fault is going to become severe. So we start with a very small fault and how it can become severe as we get along. And then safety and standards for medical devices. As I mentioned to you, Professor Tiwari will discuss the safety features and the current international standards, British standards, Indian standards for different medical devices that are being used. Now, in this particular course, the main objectives, and I would like to see at the end from you whether these objectives have been fulfilled or not. So when we conclude on the last day, we would like to go back to this slide and see whether we have managed to meet these objectives. And the objectives are, like, you should know about different classes of medical devices and their safety and performance features. You should know about international standards, regulations, and regulatory bodies for medical devices. Then you should have enough confidence and develop capability to be able to optimize the performance of medical devices. And here we'll understand the current tools that are being used right now to improve the performance. And, well, safety constraint is paramount in biology. In medical devices, safety is one of the most paramount feature. I will expose you to severe practical problems, solutions, and how we can model and simulate these medical devices. What is happening nowadays is that the technology is developing very, very rapidly, and there are newer and newer ways of analyzing the medical devices. Earlier, a product is made, and we were only concerned about its overall performance. Now we can see even the small component of that device, how that performs, and I hope with this we will have better performance, better safety of these systems. And then, last but not the least, and I think this will be mostly contributed by Professor Tiwari, to identify, control, and reduce the risk by taking adequate safety measures for these devices. So these are the objectives, and I hope by the end, and I'm reasonably sure, all these objectives will be met, and I'll be going through this slide again in the last class. So let's understand what is the meaning of medical device, and how do we, in general, how do we define? There are different standards for medical device definitions. If you go to the book, go to the websites, you'll find lots of definitions, but this is quite over-encompassing definition. So this is a device, it's an artifact, product, when used, either which can be used in the standalone condition or alongside other devices. So you can have a combination of a number of devices or a single device, which may include the software, because if you have a hardware, then you can have a software which will include the software for full implementation of the application process to be used on human beings for the purpose of. So medical device can be used standalone or alongside other devices, and it may include the software so that it can be fully implemented in the subject for the purpose of diagnosis, prevention, monitoring, treatment, or alleviation of a disease. So how can we eliminate, diagnose, prevent, monitor, treat, or alleviate a particular disease? That is the first use. Second thing is diagnosing, monitoring, treatment, alleviation, or for compensation of an injury or handicap. So it not only for the alleviation of disease, it can be used for compensation for an injury or handicap. Third, it is for investigation, replacement, or modification of the anatomy or of a physiological process. So we have anatomy and how to understand the anatomical features, any issues that are developing. So device can be used for investigating anatomy, or to replace a particular part of anatomy, modify the anatomy, or of a physiological process, and the control of conception. And which doesn't achieve, the main difference is that this doesn't achieve any of these things in or the human body by pharmacological, immunological, or metabolical means. So you are not consuming it in your system. So this is adding you externally, internally, but not in the through internal processes means, but which may be assisted in its function by such means. So we can have pharmacological, for example, if you have, or immunological or metabolical means, you have a stent, but you want to avoid the complications, like body can reject foreign material, so you can suppress that through medication, but that is not the main aim. A medical device should not achieve its principal introduction by pharmacological, immunological, or metabolical means. So this is the standard definition which is given in a number of books. So this is the definition we will govern by. Now there are lots of uses of medical devices, and in no way whatever I am saying here is complete. So there are lots of informations available, lots of uses available, but typically we use medical devices here, like in Indian context or in general, when we say medical devices, we talk about prosthetics, normally prosthetics, but like, so rehabilitation comes at the top, how the common public views it, but there are lots and lots of medical devices that are used in the human body, and we will discuss it as we go along. So use of medical devices for rehabilitation, prosthetics and all that. Then fault analysis, so like measuring blood pressure, measuring height, measuring weight, all these things can be used as a very, very simple level, faults developing into the human system. So fault analysis. Then preventive methods, medical devices are used for therapeutic applications as well, and last but not the least, palliative care. When the situation gets really, really worse, the medical devices can be used to manage the conditions at the end. So these are some of the uses I've mentioned here, although there are many other uses, but I hope these 5 uses can encompass all other uses. Just an example for how different devices are used. I'm not going to discuss all these in this particular course, but just to give you overview of bigger picture of the medical devices. So we can have medical imaging devices for in vivo diagnostics of the human body, various components like X-ray for fracture and others. We can have medical laboratory devices for in vitro diagnosis like microscopy. We can have physiological measurement devices again for in vivo diagnosis. Radiotherapy, gamma ray TC is a prime example. We can have physical therapy devices like ultraviolet, infrared and laser. And then lots of devices in surgical theater, lots and lots of devices used, right from your surgical gloves to lot many things that are used there. Disposable medical devices, so normally your injection can be a disposable medical device. And then we have devices for performance evaluation of medical devices. So you have medical devices, but you have intelligent systems embedded into those medical devices to understand the performance evaluation of those. And as I mentioned to you earlier, prosthetic implants and etc. So suppose now, based on this information, what type of idea do you make of medical devices in your mind? Right from gloves to big MRI scanner, X-rays, stents, ventricular assist devices. So these are, so it's a very, very big, wide world of medical devices, and this 2-week course will be very short if you wish to cover all such devices. Okay. So now I will consider some of the devices for further application, but I'll give you a brief overview of what is happening in the world and how we are trying to make best use of the technological breakthroughs in using these medical devices. Okay. Any questions up to this particular point? Any of you? Gloves, disposable gloves, disposable syringes, they are medical devices. So accessories is an equipment, isn't it?
There is no specific any definitions or any classification like.
So I just gave you definition here. That's what I was saying, that this definition I gave here. It's a very broad term. So I think more what you're going by is the technological sophisticatedness, isn't it? But like this is very, very elementary. Like if you give, so there are hundreds of companies make gloves. So there is lots of competition in that market, and maybe profits are smaller. But large volume is small profit. But then you get a big machine, MRI machine. There are only few companies make it, but the profits are huge. So depending upon the technological sophisticatedness, you can define that. But injection is a medical device.
Yeah, only purpose is different, but it comes under the class.
Yeah, so that is how it is defined. That's why this definition is given. So you can see under this definition you can define lots and lots of devices. But we are not going to cover every device. But there is a huge scope in working in making medical devices better. Now what I'll do is I will go through some of the medical devices and highlight, as is an introductory class, highlight some of the technical issues, and then we will go further into that. Now prosthetic implants, this is just first class of medical devices which are very common. So in prosthetic implants, what may happen is that a biological structure that may either be not functioning properly, and if a biological structure is not functioning properly, then what do we do in that case, or it may be missing completely? What do we do? In that case, we need some assistance. So prosthetic implants, they support those biological structures. They used to replace a missing biological structure or support a damaged biological structure or enhance an existing biological structure. So like for example, hip replacement, knee replacement, all such biological structures where you need a part of the body is not working, then you need to replace it or you need to strengthen it. So medical implants are typically man-made devices in contrast to a transplant, which is a transplanted biomedical issue. So these prosthetic implants is a huge market, and lots of work is being done. You must have heard about the Jaipur foot, which is a very big success in India, especially for the foot implants, like those who had amputations and all that. So then these were provided. Now here, this is particularly an area where I have been working quite in depth recently. Stents is an area where which are inserted into the damaged blood vessel, and there is lots and lots of work in even material science to develop materials or which can be used to make stents which adopt the intended shape when heated to a particular body temperature, and they take the shape of the vessel that is. Now in this particular case, the design of a stent is a unique feature here. For example, it's a mesh. Typically, we don't want metal inside the body, and the typical ratio, the upper limit is 15%. Like we should not have in a given area more than 15% of the material coming from the metal, or now lots of composites and other things. Now, what should be the structure of the stent? It should be closed like circle, or it should be open like open circle, not completed circle. So, and in this particular class, we will discuss the full implications of having different types of stents. So, we will be analyzing 3 different types of stents of different complications and see how they perform within the arterial system. We will also discuss the issues, like you can see here, plaque formation. Now, what happens is that when you put a stent there and this stent expands, this plaque formed here over the time can start to go through this stent. So what happens is that this is known as the plaque prolapse. It can go through the stent, further depositions can take place, and the intended performance of the artery is not achieved. So this is what we are going to do for 3 different types of stents. We will understand the wall shear stress and wall shear stress gradient. How do we calculate it? Lots of numerical work has been carried out into this particular area. Now I throw open a question here. For example, you have, suppose, I hope none of you have stents. I don't have a stent, and I don't want to have a stent. But suppose if it happens that that we get a stent here, I would like to know what is happening inside my body, isn't it? I would like to know how a stent inside my body is acting. Is it acting properly or not? Now, how is it possible? So I would like to have a condition where I have something on the computer that can keep telling me, oh, that you're fine, Rakesh, you're still alive. I hope you will be alive for some more time. The stent is okay. Now, in this case, the numerical simulations help a lot, because what you cannot do is you cannot have lots of equipment inside your body which can relay data to the computer or which can relay data outside. So what you can have is you can have 1 or 2 systems, like blood pressure can be easily measured, and it can be communicated through wireless and to the computer. But what we can do is we can supplement that information with simulations. You must have heard about virtual reality, augmented reality. Have you heard about this? Virtual reality, augmented reality? Like suppose if I give you Google Glass, you wear the Google Glass, look at me, and you can see my arteries here. It will be nice. The flow taking place inside the arteries. How can it be done? So suppose if I have simulation of my arteries running on the computer, and this computer is directly talking to my body through some global parameter, maybe blood pressure or something. It takes that blood pressure and simulates the flow in my arteries, and that is displayed through some sort of augmented reality function. So you can have a Google Glass and you can in situ see how the flow is taking place inside my arteries. Obviously, simulation has to be correct for that, and we have to make sure that simulation is 100% correct, and it should be fast enough to take time varying data, incorporate time varying data as the boundary condition, and give you the simulations of that. Okay. So I'm not only talking about the computational fluid dynamics, I'm talking about CFD, FEA, finite element method, flow structure interactions, all working together and giving you the total information. With the advent of Internet of Things, things are developing much faster. It's not still available. Hopefully in 10, 20 years time, we will reach a condition where we can online see how things are happening. So the problem with human body or any mechanical system is such, we can measure one parameter or two parameters or 10 parameters, but there are hundreds of parameters. If you think about human body, how many processes are going on in my body at this moment in time, or in your body? Any idea? How many processes are going in our body at this moment in time? Any ideas? No? Yes, sir, at the back? Millions of processes are going on, isn't it? Millions and millions of processes. My son works, in this particular area, so there are millions and millions of processes. And our behavior, whatever happens to us, is the outcomes of those millions and millions of processes. Now, just by measuring your blood pressure or one other parameter here, one output or two output or maybe 10 outputs cannot give us information about those 100 million processes or more processes going on in the body. This is our aim. What we see at global level, how that global information is we are getting from the local processes that are coming here. Even if we can get 100, 200 processes, that is easier enough, we can understand the outcome. But even that is difficult. This is the long-term aim. So when in the morning I was talking about digital twin, this is what I was talking about. Ultimate aim is to be able to simulate all the processes happening in your body onto the computer, which is going to be almost impossible at this moment in time. Out of millions, suppose we can do 10 or 20 or 30 or 50 most important processes on the system, and I can see on the system how those 50 processes are going on, and we can predict the performance of the human system. That will be more than enough, isn't it, for the time being? So this is what our ultimate aim is. So in this particular case, I was talking about finite element analysis to see how the stent is reacting inside the system, what type of forces are acting, radial forces are acting, how it is deforming. Then CFD part, how the flow is taking place through the arterial system with his stent, what is the velocity profile, what are the pressure pulsations, how the wall shear stress is, how the wall shear stress gradient is, so that there are lots of problems which Professor Tiwari will discuss taking place in the human body when we put stents, that those can be eliminated. Do you have any questions on this part? I hope I have thrown open a big challenge to you so that you can start thinking. Yeah. Medical implant is a medical device. Yeah, medical implant is a medical device. Okay. Any question about this? Numerical simulations, how it can be used with advantage to simulate to get the local information? No, fine. I have shown you some other examples of the medical devices. So you can see implants or devices, we are saying same thing. This implant is a medical device. So you can see here hip hemi arthroplasty, the implants for the foot, the elbow. This is robotic device for knee prosthesis implementation, and all these are examples of, they are quite diverse, but all these are examples of medical devices. So implant or device, I will name it as the same thing. Some other medical devices, I have named the word artificial organs. So cochlear implant, artificial heart, ventilator, and then we have retinal implant. So all these come as under medical device. Just to reiterate this point, the device doesn't need to be a single device. Device as a whole can be a combination of devices working. As I mentioned in the definition first, combination of devices plus software also can be part of that. So if you look at the first definition that I gave, any device when used in a standalone condition or alongside other devices, along with the software for full implementation, that is the generic definition that we give for medical devices. Okay, as I said, right from the injection gloves disposable gloves to big systems, they all come under the medical devices. Okay. Now, with regard to prosthetic devices, I must mention two words which will come in our discussion in future: active medical devices and active implantable medical device. Now, active medical device is a device which needs for its energy needs from outside. Like so, what it does it needs energy for functioning, and that source of energy is from outside. That is known as active medical devices. And active implantable medical device means that any medical devices which is intended to be totally or partially introduced either surgically or medically into human body, or by medical intervention into a natural orifice. So the two different words, sometimes these both words come, we need to understand the difference. Active medical device means it's energy based, we get energy from outside. Active implantable medical device means device which is introduced partially or fully into the human body, and which is intended to remain after the process, but it takes its energy need through an energy source. Now, a number of examples I have included here. So, for the active medical devices and active implantable medical devices, so implantable cardiac pacemaker, implantable defibrillators, implantable nerve stimulators, bladder stimulators, diaphragm stimulators, cochlear implants, and implantable active drug administration devices, implantable active monitoring devices, etc. So there are lots of examples for this. Right. Now, why it is so important? If you look at some of the data, some of the business data, some of the impact these are having on the economy. So if you look at the implant economy data from USA, the implantable defibrillators in a particular year, number of procedures done 133,262, and total annual expenditure is $5.5 billion just on the defibrillators. Artificial hips is a year data of one of the recent years, number of procedures 230,000, total annual expenditure $10.5 billion. So if you look at this, the amount of economic activity that is taking place because of these medical devices, these are staggering numbers. The staggering numbers. So better we make it. So more and more work is needed to make these devices much better, so that it becomes cheaper, affordable. Then third part is better performance and better implementation, basically. So these are some of the examples. So I have included heart pacemakers, breast implants, spine screws, intrauterine devices, metal screws, pins, plates, and rods for fracture repair. And you can see in that area the expenditure is 4.5 billion. The coronary stents, this area of my interest, is 560,000. The total annual expenditure is 7.5 billion. Ear tubes, 2 billion. Artificial eye lenses, 10 billion, because this is the more widely used. So you can see the data from the US economy, the contribution of this medical devices is huge, huge. Lots and lots of jobs, lots and lots of research is being carried out at this moment in time. Now, I would like to discuss more of a futuristic things, advancements that can be that can become quite common as we get along. As I mentioned to you earlier, the quest to reach the pinnacle of knowledge about human body is the thing that we want to reach there. How do we reach there? I would like to have, or we would like to have, a digital twin. How are we moving in that particular direction? That is what I am trying to discuss with you. So some of the advancements that are taking place through Internet of Things, because this IoT is becoming very, very popular nowadays. How through IoT this can be realized. This is what we are going to discuss. So if you look at this, the deep brain neurosimulators, cochlear implants, cardiac defibrillators, insulin pumps, foot drop implants, and gastric stimulators. All these things can be implanted in the human body, and they can communicate wirelessly. Okay, they can talk to the outside control in a wireless manner, and they can talk to each other in a wireless manner. Now think about it. Uses wise is okay, but expertise wise, how much expertise is needed here? So we need not only solid mechanics expertise, we need solid mechanics expertise, material science expertise, fluid mechanics expertise, talking as a teacher, software, electronics, and control. So all these expertise are needed. So just don't feel that a particular branch is good enough to take care of this. Lots of branches will need to work together to get this. Most of you are the PhD students or UG or what? Like, so PG students. Which branches? Biomedical engineering, isn't it? Mechanical also. So, bioinformatics. Oh, okay. So you do lots of software thing. Do you use Internet of Things there? Okay. Any electronics guy here? Electronics person? Oh, so you are here as well, isn't it? You use IoT? Internet of Things? You use IoT. Okay. So now you understand how with Internet of Things all these devices can be made to talk to each other or talk to the outside control and communicate. Ideally, the ideal scenario is like these devices are generating data. This data is communicated wirelessly through cloud. Okay? Through cloud, it is coming to your computer. Now on the computer, you have a system running which is a real replica of the physical system. And in that replica, you are putting that data in. Within that replica, you have a number of simulations ongoing. So that data is interacting with those simulations, changing the boundary conditions, for example. Okay? Now I'll give you an example simply. Suppose somehow I know how much blood is flowing in my whichever artery here. Okay? Now that if that information is available online and that information is going to cloud wirelessly, through cloud it is coming to the computer, and now I have a software simulation ongoing there which takes boundary conditions from that data. You remember, like those who have some fluid dynamics expertise, when you simulate a flow in a particular part of the body or pipe, simple pipe, it may be an arterial pipe, what boundary conditions do we need to give? So pressure or velocity, isn't it? Mass flow rate and velocity. So suppose if I know the velocity which is coming from actual system, and provided we can implement it very fast computers, we can almost get the real flow condition in the artery or in the pipeline as things go along, isn't it? That is the ultimate aim. The issue at this moment is we cannot do it immediately. Like I'll just give you the same example. It's not directly relevant to this, but slightly different example. In a football stadium, people are sitting, okay, and you have lots of sensors in the football stadium. Suddenly, one of the sensors detects some presence of some material there, okay. Now, how quickly you can develop a mitigation strategy to evacuate the football stadium? So what happens is, suppose you have simulation of the flow inside the stadium going on, you can use the sensor condition as the input to the football stadium. Then you can simulate the area of influence of the presence of that particular material, isn't it? It may be gas, it may be anything. And then based on that, you can almost get real-time dispersion of the material, and you can develop the evacuation strategy. Likewise, inside your body, I gave you the football stadium example, but like inside your body, same thing can happen. Something has gone inside your body. How far it has spread as a function of time, you can calculate. And because there are lots of complicated processes going on, it will take time before we have that type of understanding, but this type of work has already been implemented by one of the co-investigators, which implemented it in a football stadium. The main difference with the numerical simulations is the speed. The computers that you have, they are not fast enough. So there are various technologies available at this moment in time that you put pre-simulated conditions already on the computer in the data, give the boundary condition. So in place of solving, you have already solved thousands of cases on the computer already. So what you do is you pick that data from the actual condition, and that data gives you the simulated condition. So this is one way of doing it, where your machines are not faster, you have done hundreds of simulations on the computer, and you try to link. So it becomes more of a matchmaking. If I am getting this data from the body, does it correspond to that condition? But you have to be 100% sure that whatever you are doing is going to be right, isn't it? Any questions on this? Does it make sense? Any questions? Because you have diverse backgrounds, electrical, electronics, and the things. You'll be having different types of questions.
Sir, I had a question, sir,
Yeah.
regarding medical devices, sir. Sir, here, sir, what before coming to this class, a general concept about this was that something is going into the body, implantable, means it will remain inside the body. But suppose, sir, for instance, in case of bones, I was seeing other day cell-based therapy, that they are preparing scaffolds and so, sir, implant is always a non-biodegradable kind of thing, or it can be biodegradable, because sir, there is a lot of things that it is a biodegradable thing or it is a non-biodegradable.
See, the thing is, if it is consumed by the body,
Sir.
like typically what we define it is like sometimes these boundaries are very blurred because of humanizations, and which doesn't achieve its principal interaction in or on the human body by pharmacological, immunological, and metabolic means. So no metabolism is taking place, no immunological actions are there, and no pharmacological actions are there, then it will be a medical device. But if these are there, body is consuming them, then there is a problem. So then the boundaries can be quite blurred. Okay, but as like these devices keep changing, so these definitions keep changing depending upon newer and newer use. So maybe biodegradation might come sometime into play. So I don't have a specific yes or no answer, but based on this standard, these three cases, like if these three types of actions are not happening, then we call it a medical device.
Can I say something?
Yeah.
Actually, we are now having biodegradable implants also. It is having implant that is made of degradable polymers. With drug is also there. They are known as the degradable devices, multiple degradable devices for multi-purpose work. So the drug is there and degradable polymer implant is there for any prosthesis or hip joint or knee joint. What will happen in case of bone fracture? It will support the fractured bone and it will degrade after 2-3 weeks. And drug will be injected at the site of fracture for fast healing. So we can say multi-purpose fixation devices. So that is made of degradable polymers. Sutures, or you can say for tissue engineering applications. We have a matrix of degradable polymers, cells are thrown into it. And what happens when you are implanting this scaffold at the diseased place? Suppose in case of liver cirrhosis, you are implanting your tissues or cells at the disease site. What will happen? The scaffold will be placed over there and it will degrade and the cells will grow and replace the diseased cells. Like these are the
So let us be understanding in a bit more hierarchical order. So here we are talking about wearable sensors. So lots of activity is currently ongoing in the area of developing sensors, and how sensor is the main sort of ground level activity that picks up data from the human body. So what these sensors, if you can look at this, the wearable sensors, you can have RFID chip, obesity management chip, automated insulin pump, you can have drop foot stimulant, permanent prosthetic limbs, wireless cardiac defibrillator, artificial eyes, cautionary enhancement. So these come under the category of wearable sensors, and lots of these things can be worn on the human body, and these also classify as the medical devices. Again, sensors to the from the sensor which is collecting data, it is giving data to a storage device. From storage devices it is going to the computer through a cyber physical system, and then from the computer you have control of the implementation of that. After we have got the sensor and we got the different applications, next thing comes is, which is very, very important becoming nowadays as far as the research is concerned, is reliability and security of wearable and implantable devices. This is a very, very big area, especially in the electronics engineering. As we are going to have centralized data handling centers, all the data, personal data is coming from the body, is going to go into some sort of health server, and healthcare professionals can have access to your personal data to provide you with the information about that. So as you can see, lots of devices inside the human body. Then you have wireless charger to programmer, going to personal health club, to health server, and to the healthcare professional. So the reliability and security of the data is becoming a very, very big issue. So lots of work is currently ongoing on how to securely have the data security. You know that in IT security is becoming a very, very big issue, and so lots of work is currently ongoing. Generation of data is not a problem. Transmission of data is not a problem. Transmission of data securely is a problem. Okay, so that hacking is a problem. So suppose if you have a system ongoing, someone hacks onto it without physical data, then there is a problem. Especially if you have a digital twin ongoing onto the computer, someone hacks onto it, then you have a big problem. So this is another area that is becoming very, very important. Now I'll just I would like you to have a look at some of the technological changes, some of the technologies that are being currently used in this particular area. So the first thing, currently radio frequency based identification is becoming very, very important. So integrated device recognition using RFID, so using radio frequency, you can recognize the devices. Other technologies is wearable wireless sensors and devices. So you have wearable wireless sensors and devices being used. You can have implanted wireless sensors and devices. You can have ingestible sensors. You can have remote patient monitoring systems. You can have mobile medical device applications. You can have devices to assist movement of artificial limbs, and you can have video capsule endoscopy systems. So technologies are continuously being developed. We need to make them perfect, and we need to make them more and more accurate, more and more reliable, more and more fault free. And some of the things we are going to do in this particular class will take you through those particular things. So just taking a step back, I have thrown a number of words here, a number of systems, number of technologies, and now if you look at it in depth, the complications are increasing. For me to say a word is very straightforward, but the complications are enormous. Right from the sensor design, to putting sensor inside the system, to sensor operation, to the transmission of data, to data storage, from data storage to data transfer to simulation, simulation to integration of that data with the simulation, then analysis of that data, after analysis of that data, diagnosis, then intervention. So it's a very, very complicated process. And how do we get the, we all have limitations, so how do we get best out of it? So I just gave you the brief background of this, but in the next part of the course, what I'll do is I will just start with the simulations, the issues of simulation, how simulations can be used for performance evaluation of the medical devices, how through that we can understand the effect of faults, and then the biological safety features. So this will be our process that will be following now. I mentioned you about digital twin. This is one of the favorite area. I am working on digital twins right now on a number of systems, mechanical systems, and obviously people are working now on biological systems as well. So suppose this is a real hand and this is digital twin of the real hand. Okay? They use the word twins because twins have lots of what? They're very lots of similarity, but not 100%. Two twins do not have 100% similarity. They have lots of similarity, but not 100% similarity. Twins, it means they look like same. They function like same, but they're not same.
Okay, it means that their functionality, their functionality are same, but they are not.
Not 100% same though. But like one is one, the main system is main system. Twin is trying to reach that level. Okay? So one is there, other is trying to reach that level. That is the thing. So physical system is the physical system. Digital system is twin, which is trying to reach the physical system.
It means that digital system is generating the data from the real one and then behaving like that.
Digital system is trying to be like the original one. So that's why the first one I'm not talking twin. We can say they are twins, but digital one is called twin. Digital one is called twin. So digital one is the twin of the original system. Okay. Now this is the long aim, and right now all over the world, lots and lots of work is going on in creating digital twins. Lots and lots of work is going on, and it is happening for biological systems as well. What to say biological systems, even for mechanical systems, it is at the very beginning. ANSYS, current ANSYS 19.2 or something, 18 or 19.2. You know that? It has a digital twin module, which tries to create digital twins for some systems, and they are also going on to the biological systems now to create digital twins of that. So this is, I wanted to expose you to digital twins. We have done some work in that area, so I would like to share that with you, not on the biological system but for mechanical system. So the main aim is here. We have got an actual system here, and when I said I want to create a digital twin, so I just don't want to create a system that looks like a digital twin, but that acts like a digital twin. Okay, that acts like a physical system. Now, it's a very profound statement. Acts like a physical system. Acts like a physical system. When we say acts like, are we talking about globally or locally? Are we talking about globally or locally? So if you take my video, I'm being filmed, that is my digital twin, isn't it? Looks like me, talks like me, walks like me. But digital twin provides the details that are difficult to get from just general overview. So ideal situation, I want digital twin to be 100%, not 100%, okay, very much like the actual system. And the beauty comes in the local features. The digital twin that we create, that should replicate my physical system locally. Now, how locally is a question. How locally is a question. Okay, so there can be two types of analysis: macroscopic analysis, microscopic analysis. Okay, so ideally I would like it to be the microscopically similar to the physical system, but whether that can be achieved or not, that is a question. So we are trying to make digital twins that look microscopically like the actual system, and that is where the biggest difficulty at this moment is. because microscopic similarity means we have to first understand the simulation, create a mathematical model, find the solution at the molecular level, implement that on the computer, take boundary conditions for the physical system, run your simulation program, and then you can show how the two systems will be. People have done it for some specific applications, but this is a big area of research. Anything you can do in electronics and software, even mechanical systems, that will be huge work in the years to come. As you all know, 5G is going to become very popular in the years to come, and when all the devices will be interconnected, and it will open a completely new world basically, and this will impact the medical sciences or the biological systems as well. Okay, so this is what I want to discuss. Just to formalize it, in the digital twins, the virtual counterparts of the physical assets are created as digitized duplicates of machines, equipment, or physical sites using sensors. So we have sensors. These assets can be created even before an asset is built physically. This is during the product development phase. To create a digital twin of any physical asset, the engineers can collect data from different sources and then analyze from various analytic software, and all this information along with artificial intelligence algorithms is integrated into physics-based virtual models. The main